Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky. The planet Neptune. Neptune, the eighth and farthest known planet from the Sun in our solar system, is a gas giant that has intrigued astronomers since its discovery. With its vibrant blue hue and dynamic atmosphere, Neptune offers a fascinating glimpse into the outer reaches of our planetary neighborhood. This episode explores Neptune's discovery, physical characteristics, atmospheric phenomena, ring system, moons, and its importance to planetary science. Discovery and exploration. Neptune was the first planet discovered through mathematical prediction rather than direct observation. In the early 19th century, astronomers noticed irregularities in the orbit of Uranus that could not be explained by known gravitational forces. These irregularities suggested the presence of an unseen planet exerting a gravitational influence. The French mathematician Urbain Le Verrier and British mathematician John Couch-Adams independently calculated the position of the hypothetical planet using Newtonian mechanics. Their calculations were remarkably accurate, leading to the discovery of Neptune. On September 23, 1846, German astronomer Johann Galle and his assistant Heinrich D'Arrest observed Neptune for the first time at the Berlin Observatory. This discovery confirmed the existence of a planet beyond Uranus, expanding our understanding of the solar system. The most significant direct exploration of Neptune occurred in 1989 when NASA's Voyager 2 spacecraft performed a flyby. Voyager 2 provided detailed images and data, revealing much about Neptune's atmosphere, rings, and moons. This flyby remains the only close-up study of Neptune to date. Neptune is the fourth largest planet in the solar system by diameter and the third largest by mass. It has a diameter of about 49,244 kilometers, 30,598 miles, and a mass 17 times that of Earth. Despite its size, Neptune has a relatively low density, reflecting its composition of hydrogen, helium, and ices. Neptune is composed of three primary layers. 1. Atmosphere. The outermost layer, composed primarily of hydrogen, helium, and methane. The presence of methane gives Neptune its characteristic blue color, as methane absorbs red light and reflects blue light. 2. Mantle. Beneath the atmosphere lies a thick mantle of water, ammonia, and methane ices. This mantle is incredibly dense and hot, with temperatures reaching thousands of degrees Celsius. 3. Core. At the center of Neptune is a rocky core composed of silicates and metals. The core is similar in size to Earth but significantly more massive due to the high pressures and densities present at Neptune's center. Neptune possesses a strong magnetic field, which is tilted at an angle of 47 degrees relative to its rotation axis and offset from the planet's center. This irregular magnetic field is likely generated by electrical currents within the planet's icy mantle. Neptune's atmosphere is primarily composed of hydrogen, 80%, helium, 19%, and methane, 1.5%. Trace amounts of other hydrocarbons, such as ethane and acetylene, are also present. The methane in Neptune's upper atmosphere absorbs red light, giving the planet its striking blue appearance. Neptune's atmosphere features a dynamic and layered cloud structure. The upper cloud decks are composed of methane ice, while lower layers likely contain clouds of ammonia and hydrogen sulfide. The planet's deep blue color is enhanced by the scattering of sunlight by small particles in its upper atmosphere. Neptune is renowned for its extreme weather systems and high-speed winds. The planet experiences the fastest winds in the solar system, with speeds reaching up to 2,100 kilometers per hour, 1,300 miles per hour. These winds drive large storm systems and create distinct bands and spots in the atmosphere. One of Neptune's most famous atmospheric features is the Great Dark Spot, a massive storm system similar to Jupiter's Great Red Spot. Discovered by Voyager 2 in 1989, the Great Dark Spot was a high-pressure system roughly the size of Earth. However, when the Hubble Space Telescope observed Neptune in 1994, the Great Dark Spot had disappeared, highlighting the dynamic and transient nature of Neptune's atmosphere. In addition to the Great Dark Spot, Neptune hosts numerous other storm systems and vortices. These include smaller dark spots, bright clouds of methane ice, and rapidly changing weather patterns. The presence of these features indicates that Neptune's atmosphere is highly active and turbulent. Neptune's ring system was first detected in the 1960s through stellar occultation, where the rings briefly blocked the light from background stars. Voyager 2 provided detailed images of the rings during its flyby, revealing their complex structure. Neptune's rings are composed primarily of dust particles and small rocks coated with ice. These particles are likely remnants of shattered moons or comets that were captured by Neptune's gravity. Neptune has 5 primary rings, named Gal, Leverrier, Lassell, Arago, and Adams. The Adams ring is particularly notable for its bright arcs, which are denser regions within the ring. These arcs are believed to be stabilized by gravitational interactions with Neptune's moons. The Adams ring contains several bright arcs, named Liberté, Égalité, Fraternité, and Courage. These arcs are thought to be caused by gravitational resonance with Neptune's moon Galatea. which helps to maintain their structure and prevent them from spreading out. Moons of Neptune. Triton is Neptune's largest moon and one of the most intriguing objects in the solar system. Discovered by British astronomer William Lassell just 17 days after Neptune's discovery, Triton has a diameter of 2,706 kilometers, 1,680 miles, and is unique among large moons due to its retrograde orbit, meaning it orbits Neptune in the opposite direction of the planet's rotation. Triton's surface is composed primarily of nitrogen ice, with significant amounts of water ice and frozen carbon dioxide. The surface is marked by a variety of features, including plains, ridges, and impact craters, as well as active geysers that spew nitrogen gas and dust, suggesting ongoing geological activity. Triton has a thin atmosphere composed mostly of nitrogen, with trace amounts of methane and carbon monoxide. This atmosphere is extremely tenuous, with a surface pressure less than 1 part in 70,000 of Earth's atmospheric pressure. Neptune has 13 other known moons, ranging in size from small, irregularly shaped objects to larger, more spherical bodies. Some of the notable moons include Nereid, Neptune's third largest moon, discovered by Gerard Kuiper in 1949. Nereid has a highly elliptical orbit, making it one of the most eccentric moons in the solar system. Proteus, the second largest moon of Neptune, discovered by Voyager 2. Proteus has an irregular shape and a heavily cratered surface. Larissa, discovered in 1981. Larissa has an irregular shape and orbits close to Neptune's equatorial plane. The diverse characteristics and orbits of Neptune's moons suggest a complex formation and evolutionary history. Triton's retrograde orbit and geological activity indicate that it was likely captured by Neptune's gravity rather than forming in place. This capture event could have disrupted the orbits of other moons and led to the formation of Neptune's rings. Studying Neptune provides valuable insights into the formation and evolution of gas giants and ice giants in the solar system. By comparing Neptune with its neighboring gas giant Uranus, scientists can better understand the differences and similarities in their compositions, atmospheres, and magnetic fields. This comparative approach helps to refine models of planetary formation and the processes that shape the outer solar system. Neptune's extreme weather systems and high-speed winds offer a unique laboratory for studying atmospheric dynamics. Understanding the mechanisms that drive these weather patterns can provide insights into similar processes on other planets, including Earth. The transient nature of Neptune's storm systems also highlights the importance of continuous observation and long-term monitoring. Neptune's magnetic field, with its unusual tilt and offset, presents an intriguing case for studying planetary magnetospheres. the interactions between Neptune's magnetic field, solar wind, and its moons offer valuable data for understanding magnetospheric dynamics and the influence of magnetic fields on planetary environments. Neptune's location at the edge of the solar system makes it a key target for understanding the outer reaches of our planetary neighborhood. Studying Neptune and its moons can provide clues about the Kuiper belt and the processes that govern the distribution and evolution of small icy bodies in this distant region. Future exploration of Neptune. Despite the wealth of data obtained from Voyager 2, many questions about Neptune remain unanswered. Future missions to Neptune are essential for building on the discoveries made by Voyager 2 and providing a more comprehensive understanding of this distant planet. Several mission concepts have been proposed, including orbiters, flybys, and atmospheric probes. These missions aim to conduct detailed studies of Neptune's atmosphere, magnetic field, rings, and moons, as well as to explore Triton's unique characteristics and potential for habitability. Exploring Neptune presents significant technological challenges, primarily due to its distance from Earth and the harsh conditions of the outer solar system. Developing spacecraft that can withstand the extreme cold, operate at great distances from the Sun, and transmit data back to Earth requires advanced engineering and innovative solutions. Future missions to Neptune would aim to achieve several scientific goals, building on the foundations laid by previous observations and Voyager 2's flyby. Some of these goals include detailed atmospheric studies. Future missions would aim to conduct in-depth studies of Neptune's atmosphere, focusing on its composition, structure, and dynamic weather systems. Instruments capable of measuring temperature, pressure, and chemical composition at various altitudes would provide a comprehensive picture of Neptune's atmospheric processes. These studies could help explain the mechanisms behind the planet's extreme winds and storm systems, as well as the variations observed in its cloud patterns and atmospheric features. Magnetic field and magnetosphere. Neptune's magnetic field is unique due to its significant tilt and offset from the planet's rotation axis. Future missions would aim to map the magnetic field in greater detail and study its interactions with the solar wind and the planet's atmosphere. Understanding Neptune's magnetosphere, including its radiation belts and magnetic reconnection processes, could provide insights into the magnetic environments of other planets and the dynamics of planetary magnetic fields in general. Ring system exploration. While Voyager 2 provided initial insights into Neptune's rings, much remains to be learned about their composition, structure, and origins. Future missions would aim to conduct detailed studies of the rings, including the distribution and size of ring particles, the mechanisms behind the formation of ring arcs, and the interactions between the rings and Neptune's moons. High-resolution imaging and spectroscopic analysis would be essential for unraveling the complexities of Neptune's ring system. Triton and other moons. Triton, with its retrograde orbit and active geology, remains one of the most intriguing objects in the solar system. Future missions would aim to study Triton in unprecedented detail, examining its surface features, geysers, and potential subsurface ocean. Understanding Triton's geological history and its potential for hosting life could have profound implications for our understanding of habitable environments beyond Earth. In addition to Triton, Neptune's other moons would be targets for exploration. Detailed imaging and compositional analysis of moons like Nereid, Proteus, and Larissa could provide insights into their origins and evolution, as well as their interactions with Neptune's gravitational field and magnetic environment. Future exploration of Neptune would contribute to the broader field of comparative planetology, providing valuable data for comparing gas giants and ice giants within our solar system and beyond. Studying Neptune alongside other planets like Jupiter, Saturn, and Uranus helps refine models of planetary formation, atmospheric dynamics, and magnetic field generation. Additionally, Neptune's location at the edge of the solar system makes it a critical target for understanding the broader context of our planetary neighborhood. Exploring Neptune can provide clues about the Kuiper Belt, the distribution of small icy bodies, and the processes that govern the outer reaches of our solar system. Conclusion. Neptune, the distant blue giant, stands as a fascinating and enigmatic member of our solar system. From its discovery through mathematical prediction to the groundbreaking observations made by Voyager 2, Neptune has continually challenged our understanding of planetary science. Its dynamic atmosphere, complex magnetic field, intricate ring system, and diverse moons offer a wealth of scientific opportunities. As we look to the future, continued exploration of Neptune is essential for expanding our knowledge of the outer solar system and the processes that shape it. Proposed missions, equipped with advanced technology and sophisticated instruments, hold the promise of unlocking Neptune's secrets and providing new insights into the nature of gas giants and ice giants. Neptune's exploration is not just about answering specific scientific questions. It is also about broadening our horizons and pushing the boundaries of human knowledge. By venturing to the farthest reaches of our solar system, we continue the quest for understanding that has driven humanity since the dawn of civilization. The exploration of Neptune embodies the spirit of discovery, reminding us of the vast and wondrous universe that lies beyond our own planet.